Hi, welcome back. We're going to continue with our lectures on irrotational flow, and today we're going to talk about rotation and vorticity. As always, I like to show this general equation, or this general slide that shows the conservation equations, conservation of mass, momentum, and energy, just as a reminder of what the overarching governing equations are. So in today's lecture, we're going to define rotation and vorticity, and then we're going to go through some of the mathematical formulation that describes vorticity. What we're going to do is, as I said, define the vorticity and assumptions. We're going to discover how these assumptions affect shear stress, and then I'm going to present an example on rotational and irrotational vortex, and then we're going to re-examine the flow field that we examined last time, which is basically flow around a corner. So oftentimes when you think about vorticity and rotation, these are the sorts of images that people think about. Basically a big swirling flow of some sort, whether it's water draining out of a bathtub or it's a tornado somewhere. But this is not necessarily what I want you to think of when you think of vorticity and rotation. Really, this is quite a limited picture, and there's too much going on here. What I'd really rather you think about is what the shear stress is generated by this flow field. So let's find out how these two things are connected, the shear stress and the vorticity. We start with just defining the vorticity vector. So here in a 2D plane, if we are in a right-handed coordinate system, the vorticity swirls positive counterclockwise, and I'm showing it here aligned to the k direction or to the z-axis. So this is a x, y, z sort of right-handed coordinate system. In 3D, we can have the same thing, but this vorticity vector, omega, can point in any three-dimensional x, y, z or ijk reference frame. So we start by defining what the vorticity is. Vorticity, we're going to define it using this omega, and the rotation is going to be this squiggle here. And in general, or by definition I should say, vorticity is del cross v, or the curl of the velocity vector. So to say that something is irrotational is to say that the rotation or the vorticity is zero. So all irrotational flow means is that it satisfies this equation here, this del cross v, or the curl of v, is equal to 0. Notice I haven't said anything about the viscosity or the compressibility of the flow, just simply that flows that are irrotational satisfy del cross v is equal to 0. So let's expand out what del cross v is. I'm showing it here with the ijk coordinate system, x, y, z, and I'm just performed this cross product here, and on the rightmost equation you can see all of the various terms that come from this del operator crossed with the velocity vector v. And in general, I'm showing the scalar components as omega x, omega y, and omega z. So this is the scalar omega z that I had just talked about in the previous slide as the two-dimensional vorticity. So what does this mean? I think that when you notice, when you look at this vorticity written out in its ijk form, you notice that they're all cross terms, right? These are all terms like omega by y, or partial v partial z, partial v partial x. So essentially these represent or are associated with the same cross terms that appear in our shear stress. So the shear stress, the terms that define the shear stress, are the same terms that define the vorticity. And so what that means is that if the vorticity is 0, the shear stress would also be 0. So we've made the shear stress 0 without having to make the viscosity 0. So that's a fine point, but it's still one that I'd like to point out. So irrotational flows and inviscid flows are essentially similar in that they result in 0 shear stress, but they're accomplished in different ways, right? In an inviscid flow, we set the viscosity to be 0, but in an irrotational flow, we're setting the cross terms to be 0. So here's an example of two flow fields that represent vortexes. The one on the left is a rotational vortex. It's basically solid body rotation defined by this equation here, omega, capital omega r, represents the scalar velocity u sub theta. And this is essentially solid body rotation. So this would be like a log spinning around. And so the velocity increases with the radius, and the velocity is 0 at the origin of the coordinate system. On the right, we have an irrotational vortex. So it's still stuff spinning around the origin. It's defined as gamma, capital gamma, divided by r. So it's a flow field that the velocity goes to infinity at 0, and then it decays like 1 over r as we move away from the center of the coordinate system. Now, these are fundamentally different in that the one on the left is a rotational vortex and the one on the right is an irrotational vortex. Let's focus on these dots that I've got drawn here. So these blue dots for the one on the left, if you notice, they are spinning. The individual dots with these white crosshairs in them are spinning around. They appear to be spinning. If you focus just on the blue dot, they appear to spin counterclockwise, right? Each individual dot spins counterclockwise. However, the vortex on the right, if we look at an individual dot representing a particle, you can see that these particles aren't spinning. If you focus on the white dot through this orange circle, you see that it's actually just translating in a circle. So each particle isn't rotating in of itself, rather it's translating about the center in a circle. That's the distinction between an irrotational and a rotational vortex. Mathematically, we can show that the vortex on the right is 0 or has 0 vorticity, and the vortex on the left does not. So by definition, the two-dimensional vorticity comes from our cross product. Here I've written it in cylindrical coordinates because we're working in a cylindrical coordinate system. And if I calculate the vorticity for each vortex, I just simply insert the scalar velocity u sub theta here, and take the operation, multiply by r, and take the derivative with respect to r. So when I do that, you can see I get omega r squared, and I take the derivative, and I get 2r divided by r, so I end up with this just as 2 omega. So this is not 0, obviously. So it is not an irrotational flow. It's interesting also to recall by definition that omega, the vorticity, is equal to 2 times the rotation. So you can see it right here. This is the rotation. In this case, we've defined it with capital omega. And so omega would then be the rotation in this case. For the irrotational vortex, it's easy to see that if I multiply my scalar velocity by r and take the derivative with respect to r, I would just be taking the derivative of gamma. And since gamma is a constant, the derivative of this term is 0. So here I do get omega is equal to 0, or the vorticity in the z direction is equal to 0. So it does satisfy the irrotational requirement. So this is an irrotational vortex. But I think conceptually the big picture is to realize that the individual particles within this flow aren't themselves rotating. This is really a translational flow, even though it looks like it would have vorticity. All right. It's interesting to note that real vortexes, like a tornado or the drain in your bathtub, they don't really exhibit either one of these flow behaviors. In a real vortex, you wouldn't have the velocity go to infinity at 0, like you would in this irrotational vortex, nor would the velocity go to infinity as we increase the radius with this rotational vortex? So in reality, when we model real vortexes, we combine these two. We combine the linear increase in the theta velocity by utilizing a rotational vortex, and then we, at some critical radius, we decay the velocity by 1 over r. So the construction of these two is really how one would model a vortex in reality. This is a couple of images I took from Wiki, and I kind of like these, so I thought I'd show them. The Wikipedia page is also showing, to illustrate what the difference between rotational, irrotational vorticity is, they're showing the irrotational vortex and the rotational vortex, and they're also showing a parallel flow in shear. So again, this is the velocity that describes this flow field for the rotational vortex, and this is the velocity that describes the irrotational vortex. And then this is just some velocity in the xy plane. It represents just really planar shear. And what they're pointing out here, similar to what I had before, is a point. And so if we look at this point, kind of, if we think of it as just a highlighted point, we look at the velocity around it, we can see that there is a velocity field across this point, resulting in some blue translation here with a distribution of velocity around it. However, if we think of this point as a solid particle, and we think about how this particle, if we took the flow field away, how would this particle then translate through space? The particle from the rotational vortex would rotate, right? So if we had this particle and then we just took the flow field away, this particle would then tend to rotate from the inertia imparted to it. Likewise, the particle from the parallel flow field, the parallel flow with shear, would also tend to rotate because it has a positive velocity towards the bottom of the particle and a negative velocity towards the top, so the result would be some rotation or vorticity. Whereas the particle that was underflow in the that had flow around it in the irrotational vortex would really result in nothing but tension along this axis and compression along this axis. No net shear or no net rotation on that particle. All right, so to illustrate the irrotational flow field just a bit more, I'd like to return to that example that we used last time, basically defining a flow field as a planar flow field where the velocity is some constant a times x in the x direction, denoted by the unit normal I, minus ayj. So this is our velocity vector that describes the flow field, and in this case, a is equal to the constant 0.3 reciprocal seconds. I'd like you to plot and describe the flow field. Then we're going to determine if the flow field is irrotational. And then finally, I'd like to draw a box in the flow field at time 0, and then redraw it at some later time, say 1.3 seconds, and see how that box is distorted. All right, so let's start by plotting the flow field. First off, we will find the magnitude of the velocity by the vector sum, and we'll also find the angle theta by just simple geometry. And I will plot various points with at the xy location and calculate the magnitude of the velocity and the angle that this vector makes with respect to the xy coordinate system. So here are several points. Here are just kind of randomly populating the flow field, and so you can see that we're getting this kind of flow where the velocity is very high near the origin and it decays as we move away from the origin. And so the basic flow field is kind of in this direction. So what is this flow field? Really, it looks like flow around a corner, right? So the description of this flow field, just in the first quadrant, appears to be flow around the corner. If you plot it in the other quadrants, it looks very similar. All right, determine if the flow field is irrotational. Well, we have our vector components, little u and little v, and so it's quite easy just to take the cross product of del cross v. We have written out here the full vorticity vector, but since there is no velocity in the z direction, all of the terms containing w are 0, or flow in the z direction. Since there is no z direction functionality, this is planar 2D, then all of the derivatives with respect to z are 0. So we're left, just as we would think, with only vorticity in the k direction, meaning that the vector describing vorticity must point in the z direction, must be aligned to the z-axis. Whether it's 0 or not remains to be seen. So we can then write more compactly. The definition of the vorticity is del cross v as just being the omega sub z component of vorticity. We can insert the given velocity vector here and here, and take those derivatives, and you can see that it is for sure equal to 0. So this is an irrotational flow field. Finally, let's draw a box in the flow field at time equal to 0, and then let's redraw it at some later time. So we're going to start by drawing a box whose corner is at 1, 1, and 2, 2, and then redraw this and find out where these two corners basically end up somewhere later in space. So by definition, the velocity is the change. The velocity in u direction is the change in the x component with respect to t, and that is defined as ax. And the velocity in the v direction or the y direction is dy dt, which in this case was given as minus ay. We can rearrange this as a little ordinary differential equation, and we can integrate this ordinary differential equation to get a solution using the dummy variable t and dx. I've taken a little bit of liberty here with my variables, but I think that's all right. So the solution to this set of ODEs is presented here. It's just the natural log of x over x naught, the original position x naught, equals to a times tau, which represents time in this case. And so this tells us how the position xy changes of a particle which is initially at position x naught, y naught. So let's graph this. I think it's easier to just take the natural log of this, or take the exp of both sides and work with the trajectory then x and y as a function of x naught, y naught, e to the a tau. So for a point that's initially at 1 and 1 with capital A equal to 0.3 at some time later, 1.35, you can see that this point has moved to 1.5 and 2. So we can make a graph and just populate this with a variety of points, basically the corners of our box. And so we can graph this box. Here it is initially with corners at 1, 1 and 2, 2. And then at some later time here, the corners have moved to some new position. So it looks like this box is following the flow around a corner. But I think more interestingly is that we know this flow from the previous example. We know that this flow is incompressible. And we also now know that it's irrotational. So that means that box does not rotate, right? So that's what irrotational means. The box simply translated along the flow field. It did, however, distort. But because this is an incompressible flow, it means that the area of the box is conserved, right? So the initial area of the box, area naught, which would be just 2 minus 1 times 2 minus 1, the initial area is 1. Later in time, we can calculate the area again using the positions that we calculated. And again, the area is 1. So although the box has translated and distorted, it has not changed its rotation, nor has it changed its area. So we would call this just pure dilatation, just the fact that this box has stretched. In continuum mechanics, this would be just pure dilatation, and it has not rotated. All right, so that wraps up this introduction to vorticity and to rotation. And then next time we're going to derive the velocity potential function, phi, and we're going to introduce the Cauchy-Riemann equations. So look forward to it next time. Talk to you later. Bye.